issues of events of uncertainty, and so the rule of the axioms of probability, that's where we would start. There are three basic axioms. Axioms are, so the first axiom is probability of the whole set is 1. And that makes sense because when you perform an experiment, something needs to happen. So the set is, after all, is the collection of events. So psi 1, psi 2, these could be the outcomes. And combining some of them, you could also have sets A, B, etc. So sets are events. The psi's are elementary events. And another axiom of probability, that the probability of any set is a non-negative number. Probability of the whole set is 1. The third axiom is if two events are mutually exclusive, in other words, if their intersection is empty, then the probability of their union is the sum of the probabilities. So is the sum of the probabilities. From set theory, you can see clearly this makes sense, because if two events are mutually exclusive, A and B are like this, so they have nothing in common. That's what mutual exclusiveness. So the probability of their union is the sum of the probabilities. Now, we don't question the axioms by the very nature. So now the whole idea is that anything else we need to evaluate from these axioms. So to give you an example, so the question is, what is the probability of A complement? Or if A and B are, let's say, is not mutually exclusive, then what is the probability of their union? Things like this. So everything we need to derive from here. So I'll show you these quickly. Probability of A union A bar is whole set, but A and A bar are mutually exclusive. So using axiom number 3, we get probability of A union A bar is PA plus PA bar. I've used axiom number 3 here, but this is equal to probability of S, and from axiom number 1, this is 1. So you get PA bar is 1 minus PA. This is what I mean by a proof. Similarly, if you want to do the other one, so this is a case where A and B are not mutually exclusive. So they are like this. A is here, B is here. And so this region is A union B. I'm sorry, A intersection B, this region. So notice that A union B, you can also write it as A and A union A bar B, because A bar B is this region. This is A bar B. Everything outside A intersection with B will give you A bar B. The reason I'm writing like this is because these two are mutually exclusive, as you can see from here. So the probability of these two sets, the union of this is the probability of this. But now we can use axiom number 3 and write this as PA plus P A bar B. And so that's one thing. Now PA bar B is here, but notice that from here we also can write B as AB union A bar B, just by observation. The set B is this union with this. But once again, these two are mutually exclusive. So from here, using axiom number 3, we get PB as PAB plus PA bar B. And from here, if you eliminate PA bar B by is PB minus PAB and substitute it here, we get PA union B as PA plus PB minus PAB. So that's the case when A and B are not mutually exclusive. Now, so moving on, next we will discuss another concept called conditional probability. So conditional probability is, this is when something has occurred. Let's say B has occurred. So this is in the when there is a lot of uncertainty but you have some information about B. In fact, B has occurred. Question is, what more can you say about PA? Can you update this in the light of this? So that's where the conditional probability comes of. So we read this as probability of A given B, given because B has occurred. And the definition is PAB over PB. This is the definition. But the question is, does this definition make sense? And so we have to make sure that the three axioms are satisfied. Are they satisfied, right? So let's check one by one. The first axiom is that the probability of, we substitute here the whole set. So probability of the whole set intersection B is PB. PB over PB is 1. So the first axiom is satisfied. The second axiom says the probability should be non-negative. Both are non-negative numbers, so that's also satisfied. Third axiom says if this is a C intersection, this is such that the A is such that C union B, whereas C union D, let's say, C union D, union. Whereas C intersection CD is 0, in other words, C intersection C is 0. Then according to X, so let's see what happens with that. So I'm just going to use here. So that's A is now C union D, intersection with the B over PB. But the numerator we can expand it as PCB union PDB divided by PB. But CB and DB are mutually exclusive because C and D are mutually exclusive. So the probability of this union is the sum of the probabilities. But then once again, if you use the axiom, the definition of the conditional probability, we can write this as in this manner. So the summary is now that this actually satisfies the third axiom also. So this definition is a useful definition. And so just before I conclude, let me introduce one more notion, which is the notion of independence. So we have the axioms of probability, and then conditional probability, and then independence. So we say A and B are independent if the probability of their intersection is the product of their probabilities. So this need to be checked. So this is just a probabilistic notion. So if you have the three probabilities, you can check and see whether it is yes and no. But one quick observation is that if A and B are independent, then the conditional probability is PAB over PB. But PAB is PA multiplied by PB from here. So PB cancels and you get PA. So what that means is if A and B are independent, then conditioning, even if the fact that B has occurred, is not going to improve our knowledge about PA. And you can also show that if A and B are independent, you can see A bar and B are independent, etc. So I'm going to leave it as an exercise to show A bar, B bar are independent, and so on.